Now, in this lecture, we'll find out the area of the circle. In the drawing, we have quadrilateral ABCD. Inside this quadrilateral, we have this circle. You know that side AB equals to 2 units in its length, side BC also side BC equals to 8 units, and side DC also equals to 8 units in its length. This angle ABC equals to 90 degrees, and this angle DCB also equals to 90 degrees. Our mission is to find out the area of this circle. So first of all, we'll do a construction. We'll extend side DA and side CB by straight line until they touch each other. So actually, this is the touching point between the two sides. We define the touching point as M. CB, it is one side of quadrilateral ABCD, therefore it is absolutely a straight line. When you extend the straight line CB by a straight line, the result must be a straight line, therefore CM is also a straight line. So if we focus on the upper side of the straight line CM at point B, here the sum of the angles must be equal to 180 degrees according to the rule that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of CB at point, or the upper side of CM at point B? We have this angle that is equal to 90 degrees plus the missing angle. In total, they must be equal to 180 degrees. Therefore, the missing angle must be equal to 90 degrees. Again, in order to complete the sum of the angles on the upper side of CM at point B to 180 degrees, the missing angle here must be equal to 90 degrees. In the next step, we define angle AMB as theta. We focus on triangle AMB. In this triangle AMB, this angle equals to theta. This angle equals to 90 degrees. Therefore, the missing angle here must be equal to 90 degrees minus theta. Why? Because 90 degrees minus theta plus theta, it is 90 degrees, and 90 degrees plus 90 degrees, it is 180 degrees. That is the sum of the angles in any triangle. Likewise, in the big triangle MDK, here, this big triangle, AMDC, this angle equals to theta, this angle equals to 90 degrees, therefore the missing angle here must be equal to 90 degrees minus theta. In the next step, we will prove that the big triangle MDC is similar to the small right triangle MAB. So, I write it down. The big triangle MDC, the big right triangle MDC is similar to the small triangle MAB. So, why those two triangles are similar to each other? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. So, this angle is actually angle DCB in the angle DCM in the big triangle. Is equal to this angle that is actually angle ABM in the small triangle. They are both equal to 90 degrees, therefore they are equal to each other. So I repeat again. angle DCM in the big triangle equals to angle ABM in the small triangle. They are both equal to 90 degrees, therefore they are equal to each other. In addition, this angle theta is the common angle that belongs to both triangles, so angle theta equals to itself. So angle theta in the big triangle is defined as angle DMC. And it is equal to angle theta itself. In the small triangle, angle theta is defined as angle AMB. Okay, again, angle DCM, that is angle theta, equals to angle AMB, that is also theta. So it is a common angle that belongs to both triangles, therefore angle theta equals to itself. And finally those two angles are both equal to 90 degrees minus theta, therefore they are equal to each other. So angle MDC in the big triangle equals to this angle MAB in the small triangle. They are both equal to 90 degrees minus theta, therefore they are equal to each other. Repeat again. Angle MDC in the big triangle equals to angle MAB in the big triangle, and angle MDC in the big triangle equals to angle MAB in the big triangle, and to angle MAB in the small triangle. They are both equal to 90 degrees minus theta, therefore they are equal to each other. So actually proved that all three angles in the big triangle MDC equals to all the correspondingly to all the three angles in the small triangle MAB. Therefore, triangle MDC, the big triangle, is similar. This is the sign of similar to the small triangle MAB according to angle similarity rule. So what is angle similarity rule? Angle similarity rule is that if you prove that all three angles in one triangle are correspondingly equal to all the three angles in another triangle, then you actually prove that the two triangles are similar to each other according to angle similarity rule, exactly as we proved here. From the fact that the two triangles are similar to each other, we conclude that the following relationship exists between their sides. That MC in the big triangle over AMB in the small triangle equals to DC in the big triangle over AB in the small triangle. Repeat again. MC over MB equals to DC over AB. What is the length of MC? From the drawing it is very easy to see that MC equals to MB plus BC. So I write it down. MC equals to, we substitute MC by MB plus BC over MB equals to DC. DC equals to 8 units. We substitute DC by 8 and over AB. AB is 2, so we substitute AB by 2. In conclusion, we found out that MB plus BC equals MB plus BC over MB equals to 8 over 2. BC equals to 8 units and 8 over 2 is 4. Here BC equals to 8 units in its length. BC equals to 8 units in its length. So MB plus BC, that is 8 over MB equals to 8 over 2 is 4. So if we found out that MB plus 8 over MB equals to 4, we will multiply this equation by MB, and we get that MB plus 8 equals to 4 times MB. Here we subtract MB from this equation, and finally we get that 8 equals to 4MB minus MB, it is 3MB. Here we divide this equation by 3, and finally we get that MB equals to 8 over 3. MB equals to 8 over 3, so I can write here that this side MB equals to 8 over 3 units. In the next step, we will implement the Pythagoras theorem on the right triangle AMB. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse in the right triangle AMB is AM. Therefore, the square of the hypotenuse is AM squared. And it must be equal to the sum of the squares of the perpendiculars, that is to say, it must be equal to AB squared plus MB squared. Repeat again. According to the Pythagoras theorem, in the right triangle AMB, AM squared equals to AB squared plus MB squared. So AM squared equals to AB squared. AB is 2, therefore AB squared is 2 squared, that is 4, plus MB squared. We just right now found out that MB equals to 8 over 3, therefore MB squared equals to 8 over 3 squared. So AM squared, the square of the hypotenuse, equals to 4 plus 8 over 3 squared, it is 8 squared, that is 64, over 3 squared, that is 9. So AM squared equals to 4 plus, actually, we multiply 4 by 9, and then we divide it by 9 in order to have a common factor with 64 over 9. So 4 times 9 is 36. 36 plus 64 over 9. So actually found out that AM squared equals to 36 plus 64, it is 100 over 9. So here we'll take a root out of this equation, and finally we get that AM equals to the square root of 100 over 9. The square root of 100 is 10, and the square root of 9 is 3. So in conclusion, found out that AM equals to 8 over 3. So you can write down the original drawing that AM equals to 8 over 3 units. In the next step, I present to you a new rule, and we'll implement a new rule in our drawing. According to rule number 1, a tangent to a circle is perpendicular to the radius drawn to its point of tendency. Here, tangent AB is tangent to this circle at point M. Point M is the point of tendency. And we have the radius OM that is drawn to the point of tendency, that is to say it is drawn to point M, that is the point of tendency. Therefore, according to rule number 1, the tangent AB will be perpendicular to the radius MO. That is to say this angle equals to 90 degrees and this angle equals to 90 degrees according to rule number 1. So whenever you have a radius that is drawn to the point of tendency, then the tangent will be perpendicular to that radius. In this case, it means that this angle will be equal to 90 degrees and this angle will be equal to 90 degrees. So we can implement rule number 1 in our drawing. We define the center of the circle as O. We define the point of tendency of tangent AB with this circle as M. We join points O and M together by a straight line. Point O is the center of the circle, point M is the point of the circle itself. This is exactly the definition of a radius. So OM is the radius of the circle that we define as X. Here, according to rule number 1, we have the radius OM that is drawn to the point of tendency, that is to say it is drawn to point M. That is the point of tendency of tangent AB with the radius with this circle. Therefore, the tangent AB will be perpendicular to MO. So AB perpendicular to MO. That is to say this angle equals to 90 degrees and this angle will be also equal to 90 degrees according to rule number 1. We have here side BC is tangent to this circle at this point. We define the point of tendency as N. We join points O and N together by a straight line. Point O is the center of the circle, point N is the point of the circle itself. This is exactly the definition of a radius. Therefore, ON is the radius of the circle. Again, the radius ON is drawn to the point of tendency, that is to say it is drawn to point N, that is the point of tendency of tangent BC with the circle. Whenever a radius that is drawn to the point of tendency, then tangent BC will be perpendicular to the radius NO. So BC is perpendicular to NO according to rule number 1. That is to say this angle equals to 90 degrees and this angle equals to 90 degrees according to rule number 1. So here we created actually quadrilateral MOBN. Inside quadrilateral MOBN we have 1, 2, 3 right angles. The sum of 3 right angles is 90 times 3 is 270 degrees. Plus the missing angle. In total, the sum of those 3 angles must be equal to 360 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, the missing angle here must be equal to 90 degrees. 270 degrees plus 90 degrees is 360 degrees. That is the sum of the angles in any quadrilateral. Okay. In the next step, we'll do a construction. We'll build perpendicular on BC in such a way that it will be also tangent to the circle. We'll define the touching point of the perpendicular and BC as L. So this angle equals to 90 degrees and this angle equals to 90 degrees according to our construction. We define the point of tendency of the perpendicular from point L and the circle as G. So we have here tangent MG, it is tangent to the circle at point G. We join points O and G together by a straight line. So here point O is the center of the circle. Point G is the point of the circle itself. Therefore, OG is the radius of the circle that is equal to X according to our definition. Again, we have the radius OG that is drawn to the point of tendency, that is to say it is drawn to point G, that is the point of tendency of tangent G with this circle, and according to rule number 1, whenever you have a radius that is drawn to the point of tendency, then the tangent NG will be perpendicular to the radius OG. That is to say this angle will be equal to 90 degrees, and this angle will be also equal to 90 degrees. We will focus on quadrilateral ONLG. Inside quadrilateral ONLG, we have 1, 2, 3 right angles. Therefore, according to what I explained a couple of minutes ago, here the missing angle must be equal to 90 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. So, here we have line segment MG. We have line segment MG. Angle GOM equals to 90 degrees plus 90 degrees, it is 180 degrees. So angle GOM equals to 180 degrees. Any angle that is equal to 180 degrees must be a straight line. Therefore GOM is a straight line. So you can write down that line segment GOM is a straight line. GOM is a straight line. If GOM is a straight line, then GM is also a straight line. So GM, line segment GM is a straight line. Line segment GM touches the circle at points M and G. Therefore, line segment MG that is a straight line, this is a chord. Line segment MG, it is a chord that passes through the center of the circle. Okay, so GM is a chord that passes through the center of the circle. That is to say for point O, that is the center of the circle. Center of the circle, point O. Yeah. Center of the circle is point O. And you know that any chord that passes through the center of the circle must be the diameter of the circle. Therefore, we will conclude that GM is the diameter of the circle. But we know that the radius of this circle equals to x according to our definition, therefore the diameter must be twice of as the radius, that is to say GM. But first of all, GM is the diameter of the circle, and here we focus on quadrilateral MGBL. On this quadrilateral, the big quadrilateral MGBL. Inside quadrilateral MGBL, we have 1, 2, 3, 4 right angles. Any quadrilateral that has 4 right angles must be at least a rectangle. So we relate to quadrilateral MGBL as a rectangle. If quadrilateral MGBL that has 4 right angles must be at least a rectangle. So we relate to quadrilateral MGBL as a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. That is to say, in rectangle MBGL, side MG must be equal to side BL. MG equals to BL. Repeat again. In rectangle MGBL, the opposite sides are equal to each other, that is to say MG equals to BL, but we have already found out that MG is the diameter of the circle. From this equation BL equals to MG equals to the diameter, we will derive that BL is also the diameter of the circle. The diameter is twice as long as the radius, but the radius of this circle is x according to our definition. Therefore, BL equals to 2x. BL equals to 2x. You can write down in the original drawing that in this line segment BL equals to 2x in its length. BL equals to 2x. Okay, so in the next step, we'll extend the perpendicular LG until it touches side MD. And we define the touching point of the extended LG and side MD as K. So in the next step we will prove that triangle MKL is similar to the small triangle MAB. Inside the big triangle MKL, we have this angle equals to theta. This angle equals to 90 degrees, therefore the missing angle must be equal to 90 degrees minus theta. According to the same explanation that 90 degrees minus theta plus theta is 90 degrees, and 90 degrees plus 90 degrees is 180 degrees, that is the sum of the angles in any triangle. Repeat again, we prove that the big right triangle MKL is similar to the small right triangle AMB. So, why those two right triangles are similar to each other? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. So you can write down that angle KLM in the big triangle equals to this angle ABM in the small triangle. They are both equal to 90 degrees, therefore they are equal to each other. Repeat again. Angle KLM in the big triangle equals to angle ABM in the small triangle. They are both equal to 90 degrees, therefore they are equal to each other. In addition, this is angle theta. It belongs to both triangles. It is a common angle that belongs to both triangles. So actually angle theta equals to itself. Angle theta in the big triangle is angle KML. And it is equal to angle theta itself. Angle theta in the small triangle, it is defined as angle AMB. Repeat again. We called to angle theta two different names. Angle theta, it is angle KML, and it is equal to angle theta itself, that is also can be defined as angle A and B. Angle theta is a common angle that belongs to both angles, so angle theta equals to itself. And finally, those two angles are both equal to 90 degrees minus theta, therefore they are equal to each other. So this is angle MKL in the big triangle, and it is equal to this angle. This is actually in the small triangle, angle MAB. They are both equal to 90 degrees minus theta, therefore they are equal to each other. Repeat again. Angle MKL in the big triangle equals to angle MAB in the small triangle. They are both equal to 90 degrees minus theta, therefore they are equal to each other. So we actually proved that all the three angles in the big triangle are correspondingly equal to all the three angles in the small triangle. Therefore, the big triangle MKL is similar to the small triangle, triangle AMB, according to angle similarity rule. And from the fact that the two right triangles are similar to each other, we conclude that the following relationship exists between their sides. We conclude that ML in the big triangle over MB in the small triangle equals to KL in the big triangle over AB in the small triangle. I'll repeat again. ML over MB equals to KL over AB. From the drawing, it is very easy to see that ML equals to MB plus BL. That is to say, ML equals to MB, that is 8 over 3, plus BL, that is 2x. So we substitute ML by 8 over 3 plus 2x. Divided by MB. It is equal to KL. KL is the missing side, so we leave it as it is. Over AB. AB equals to 2 units according to what is given as the equation, so we substitute AB by 2. In conclusion, we found out that 8 over 3 plus 2x over MB equals to KL over 2. We'll multiply 2x by 3 and then we divide it by x in order to have a common factor with 8 over 3. And we'll get that 8 over 3. 2x times 3 is 6x. So 6x over 3 over MB. Over MB. MB equals to 8 over 3. So we substitute MB by 8 over 3. And it is equal to KL over 2. So here we have 3 in the numerator and 3 in the denominator, so 3 will get cancelled, and we will get finally that in this side of the equation we have 8 plus 6x over 8 is equal to KL over 2. Here we'll cross multiply this equation and we get that 2 times 8 plus 6x equals to 8 times KL. We'll divide this equation by 2 and we get that 8 plus 6x equals to 8 over 2 is 4. So it is 4 KL in total. Here we divide this equation by 4 and finally we get that KL, the missing side, is equal to 8 over 4 is 2 and 6x over 4 is 1.5x. So in total we found out that KL equals to 2 plus 1.5x. So we write it down in the drawing, in the original drawing, that this line 7 KL is equal to 2 plus 1.5x. Here, again, I found out that the big triangle MKL is similar to the small triangle MAB. Therefore, we can actually conclude that another relationship exists between their sides. We conclude that ML in the big triangle over MB in the small triangle equals to MK in the big triangle over MA in the small triangle. Repeat again. ML over MB equals to MK over MA. Here, I put again that ML is equal to MB plus BL. MB is 8 over 3 and BL is 2x. Therefore, in total, ML equals to 8 over 3 plus 2x. So we substitute ML by 8 over 3 plus 2x over MB. MB is 8 over 3, so we substitute MB by 8 over 3. And it is equal to MK. From drawing, it is very easy to see that MK equals to MA plus AK. Again, MK equals to MA plus AK. So MK equals to MA, that is 10 over 3 plus AK. So we substitute MK by 10 over 3 plus AK. Over MA, that is 8 over 3, so we substitute MA by 8 over 3. In conclusion, we found out that 8 over 3 plus 2x over 8 over 3 equals to 8 over 3 plus 8k over 8 over 3. So here we'll multiply 2x by 3 and then we divide it by 3 in order to have a common factor with 8 over 3. And here also we'll multiply 8k by 3 and then we'll divide it by 3 in order to have a common factor with 10 over 3. Okay, so we'll get that 8 over 3, 2x times 3 is 6x over 8 over 3 is equal to 8 over 3. 8k times 3 is 3k plus 3k over 8 over 3. So here we have 3 in the numerator and 3 in the denominator, so 3 will get cancelled. Here we have 3 in the numerator and 3 in the denominator, so 3 also will get cancelled. What is left from the equation after we cancelled 3 on both sides of the equation? Here we have 8 plus 6x over 8 it is equal to a 10 plus 3 times AK over 10. Okay, so here we cross multiply this equation and we get that 10 times 8 plus 6x equals to 8 times 8 plus 3ak. So here we'll open the brackets on both sides of this equation and you get that 8 times 10 is 80 plus 8 times 6x is 60x and it is equal to 8 times 10 is 80 plus 8 times 3ak, it is 24ak. Here we have 80 in both sides of the equation, so 80 will get cancelled and we left only with 60x. It is equal to 24ak. Here we divide this equation by 24 and finally we get that ak equals to 60x over 24, it is 2.5x. So in conclusion, found out that this line segment AK equals to 2.5x. Okay, so in the next step I will copy quadrilateral AKLB in a new page and we'll analyze it. So actually this is quadrilateral AKBL that they copied from the original drawing. We have this quadrilateral blocks this circle. This circle is blocked by the quadrilateral AKBL. So I copy this circle. Yeah. So this is the circle that is blocked by quadrilateral AKBL. This circle is tangent to the quadrilateral in 4 points. This is the first point. We will define the first point as M, the point of tendency. We define the second point of tendency between the quadrilateral and the circle as M. We define this first point of tendency between the circle and the quadrilateral as N. And we define the fourth point of tendency between the quadrilateral and the circle as O. So in the next step I will present to you a new rule and we will implement the new rule in our drawing. We have actually rule number 2. According to rule number 2, the lengths of two tangents from a common external point to a circle are equal. We have the common external point, point P. From the common external point, point P, we draw two tangents to this circle, tangent PA and tangent PB. Tangent PA tangent to the circle is point A, and tangent PB tangent to this circle is point B. According to this rule, whenever you draw two tangents from a common external point to a circle, then the lengths of the two tangents will be equal to each other. That is to say, PA equals to PB. So we can implement the new rule, rule number 2, in our drawing. We we'll focus on point A. Point A is a common external point in relation to this circle. From the common external point, point A, we have two tangents to this circle, tangent AL and tangent MA. And according to rule number 2, tangent AL must be equal to tangent AM. So if AL is A, then MA must be equal to A because they are equal to each other. In the next step, we'll focus on point B, on the common external point, point B. Point B is the common external point in relation to this circle. From the common external point, point B, we have two tangents to this circle, tangent BM and tangent BN. And according to rule number 2, tangent BM must be equal to tangent BN. So if BM is B, then BN must be also equal to B. So here BM equals to BN equals to B. In the next step, we'll focus on the common external point, point L. From the common external point, point L, we have two tangents to this circle, tangent LN and tangent LO. And according to rule number 2, LN, tangent LN must be equal to tangent LO because they are exiting from the same common external point, point L. LN equals to LO. So if NL is C, then LO must be also equal to C. So LN equals to LO equals to C. And finally, we'll focus on the common external point, point K. From the common external point, point K, we have two tangents to this circle, tangent KL and tangent KO. And according to rule number 2, tangent KL must be equal to tangent KO. So if KL is D, then KO must be also equal to D. Okay, yeah. So in the next step, we will add side AK with side BL. Okay, so here we have side AK of the quadrilateral AKBL plus side BL. AK equals to A plus D, so we substitute AK by A plus D. And BL plus BL. BL equals to B plus C. So we substitute BL by B plus C. The conclusion is found out that AK plus BL equals to A plus D plus B plus C. That is to say, is actually equals to A plus B plus C plus D. In the next step, we will add side AB with side KL. Side AB plus side KL. Side AB equals to A plus B, so we substitute AB by A plus B plus side KL. Side KL equals to C plus D. Again, side KL equals to C plus D. So here, AK plus BL equals to A plus B plus C plus D, and AB plus KL also equals to A plus B plus C plus D. Therefore, we conclude that AK plus BL equals to AB plus KL. Okay, those two sides, those two AK plus BL equals to AB plus KL because both of them are equal to A plus B plus C plus D. So we can write down that AK plus BL equals to AB plus KL. Okay. So here AK equals to 2.5x, so substitute AK by 2.5x. BL here, BL equals to 2x. BL equals to 2x, so substitute BL by 2x. And it is equal to AB. AB equals to 2 units according to what is given us in the question. So substitute AB by 2 plus KL. We already found out that KL is 97 KL equals to 2 plus 1.5x. So we substitute KL by 2 plus 1.5x. Okay. So we found out that 2.5x plus 2x equals to 2 plus 1.5x. 2.5x plus 2x is 4.5x. 2 plus 2 is 4. So in total, in this subset of the equation, we have 4 plus 1.5x. Here we subtract 1.5x from this equation, and finally we get that 4.5x minus 1.5x equals to 3x is equal to 4. 3x equals to 4. We'll divide this equation by 3. And finally we get that x equals to 4 over 3 units. That is to say the radius of this circle x equals to 4 over 3 units. And we also know that the area of any circle, here the square brackets is the sign for the area, so the area of any circle equals to pi times the radius squared, pi all squared. In our case, the radius of our circle will be equal to pi. R is x, so r squared is x squared. So it is pi, and x equals to 4 over 3. So we substitute x by 4 over 3. X is 4 over 3, therefore x squared is 4 over 3 squared. So the area of our circle equals to pi times 4 over 3 squared. 4 over 3 squared is 4 squared, that is 16. Over 3 squared, that is 9. In conclusion, we found out that the area of our circle is 16 pi over 9 square units, or in terms of numbers, it is equal to 5.585 square units, and that is the answer to our question. Repeat again, the area of this circle, that is the area that we are looking for, equals to either 16 pi over 9 square units, or in terms of numbers, the area of this circle equals to 5.585 square units. In the next step, I will summarize the lecture. In this lecture, I found out the area of this circle. Actually, in the drawing we have quadrilateral ABCD. Inside this quadrilateral, actually, this is quadrilateral ABCD. Inside this quadrilateral we have this circle. We know that side AB equals to 2 units in its length, side BC equals to 8 units in its length, side DC equals to 8 units in its length. And this angle ABC equals to 90 degrees. This angle TCB also equals to 90 degrees in its length, in its size. Our mission is to find out the area of this circle. In order to find out the area of the circle, we extended side DA and side CB of the quadrilateral ABCD by a straight line until they touch each other at point M. We find the touching point of the two sides of this point M. So CB is a straight line. We extended the straight line CB by a straight line, therefore CM must be also, the result CM must be also a straight line. If we focus on the upper side of the straight line CM at point B, the sum of the angles must be equal to 180 degrees. Which angles we have at the upper side of CM at point B? We have this angle that is equal to 90 degrees plus the missing angle. In total, they must be equal to 180 degrees. Therefore, the missing angle must be equal to 90 degrees. Okay, this angle ABM equals to 90 degrees. Then we define this angle as theta. So in the right triangle ABM, this angle equals to theta. This angle equals to 90 degrees. Therefore, the missing angle must be equal to 90 degrees minus theta. Why? Because 90 degrees minus theta plus theta, it is 90 degrees. And 90 degrees plus 90 degrees, it is 180 degrees. It is the sum of the angles in any triangle. Likewise, in the big triangle MDK, in the big right triangle MDK, this angle equals to theta. This angle equals to 90 degrees. Therefore, exactly for the same reason, the missing angle here must be equal to 90 degrees minus theta. Then we prove that the big triangle MDC is similar to the small triangle MAB or MBA. Why those two right triangles are similar to each other? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. In addition, this angle theta is a common angle that belongs to both triangles, so angle theta equals to itself. And finally, those two angles are both equal to 90 degrees minus theta, therefore they are equal to each other. So I actually found out that all the three angles in the big triangle MDC are correspondingly equal to all the three angles of triangle MAB. Therefore, the two right triangles are similar to each other according to angle similarity rule. And therefore, the following relationship exists between their sides. MC in the big triangle MC in the big triangle over MB in the small triangle equals to DC in the big triangle over AB in the small triangle. Repeat again. MC over MB equals to DC over AB. From the drawing, it is very easy to see that MC equals to MB plus BC. That is to say, MC equals to MB, that is 8 over 3 plus BC, that is equal to 8 units according to what is given as the equation. So we can substitute MC by 8 over 3 plus 8 over 3 plus 8. Here actually MC equals to MB plus BC. So MB is unknown, so MC equals to MB plus BC, that is 8. So we can substitute MC by MB plus 8. Yeah, we substitute MC by MB plus BC, but BC is 8, therefore we substitute MC by MB plus BC, that is 8. DC equals to 8 units and AB equals to 2 units. This is 8, BA is 2. So in conclusion, found out that MB plus BC over MB equals to 8 over 2. 8 over 2 is 4. So MB plus BC, that is 8 over MB equals to 4. We multiply this equation by 4 and finally we found out that 4 times MB equals to MB plus 8. We subtracted MB from this equation and finally we found out that 8 equals to 4MB minus MB, it is 3MB. 4 equals to 3MB, we divided this equation by 3 and we found out that MB equals to 8 over 3 units. Here this side MB equals to 8 over 3 units in its length. Then we implemented the Pythagoras theorem on the right triangle A and B. According to the Pythagoras theorem, on the right triangle A and B, the square of the hypotenuse equals to the sum of the squares of the perpendiculars, that is to say AM square equals to AB square plus BM square. Repeat again, in the right triangle A and B, AM square equals to AB square plus MB square. So AM square equals to AB square. AB is 2, so AB square is 2 squared, that is 4, plus MB square. We just right now found out that MB equals to 8 over 3, therefore MB square equals to 8 over 3 square. In total, we found out that AM square equals to 4 plus 8 over 3 square, so AM square equals to 4, plus 8 over 3 square is 8 squared, that is 64, over 3 squared, that is 9. So AM square equals to 4 plus 64 over 9. We multiplied 4 by 9, and then we divided by 9 in order to have a common factor with 64 over 9. 4 times 9 is 36, plus 64 over 9. Okay, and 64 plus 36 is 100 over 9 equals to AM square. We took out of this equation and finally found out that AM equals to the square root of 100 is 10 and the square root of 9 is 3. In conclusion, we found out that AM equals to 10 over 3. Here, AM equals to 10 over 3 units. Then I presented to you a new rule and implemented the new rule in our drawing. We have actually rule number 1. According to rule number 1, a tangent to a circle is perpendicular to the radius drawn to its point of tangency. AB is tangent to this circle at point M. Point M is the point of tendency. We have the radius OM that is drawn to the point of tendency, that is to say it is drawn to point M, that is the point of tendency. Therefore, tangent AB will be perpendicular to OM. So if AB is perpendicular to OM, it means that this angle equals to 90 degrees and this angle equals to 90 degrees according to rule number 1. Implemented rule number 1 in our drawing. AB is tangent to this circle at point M. You join points O and M together by a straight line. Point O is the center of the circle, point M is the point of the circle itself, therefore OM is the radius that we defined as X. The radius OM is drawn to point M, that is the point of tendency, therefore the tangent AB will be perpendicular to MO according to rule number 1, therefore this angle equals to 90 degrees and this angle equals to 90 degrees. PL is tangent to the circle at point M. Point N is the point of tendency. We join points O and N together by a straight line. Point O is the center of the circle, point N is the point of the circle itself, therefore ON is the radius of the circle, that is equal to X according to our definition. We have the radius ON that is drawn to the point of tendency, that is to say it is drawn to point N. Therefore, according to rule number 1, this angle equals to 90 degrees and this angle equals to 90 degrees. In the next step, we actually draw perpendicular on BC in such a way that it will be also tangent to the circle at point G. So this angle equals to 90 degrees and this angle equals to 90 degrees according to our construction. We have tangent LG. We join points O and G together by a straight line. Point O is the center of the circle, point G is the point of the circle itself, therefore OG is the radius. The radius OG is drawn to point G, that is the point of tendency. Therefore, tangent NG will be perpendicular to the radius GO. That is to say, this angle equals to 90 degrees and this angle equals to 90 degrees according to rule number 1. So in triangle and quadrilateral OGLN, we have 1, 2, 3 right angles, therefore the fourth angle must be equal to 90 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Likewise, in quadrilateral OMBN, we have 1, 2, 3 right angles, Therefore, the fourth angle must be also equal to 90 degrees according to the same rule. So we have here line segment GM. Line segment GM, angle GOM equals to 90 degrees plus 90 degrees, it is 180 degrees. And because of the fact that angle GOM equals to 180 degrees, any angle that is equal to 180 degrees must be a straight line. Therefore, GM is a straight line, but GM touches the circle at point G and M. Therefore, it is defined as a chord. GM is a chord that passes through point O, that is the center of the circle. Any chord that passes through the center of the circle must be the diameter of the circle. Therefore, GM is the diameter of the circle. Okay. So here, GM is the diameter of the circle. And of course, as I already mentioned before, GM is a straight line. So if we focus on triangle on quadrilateral MBLG, we have 1, 2, 3, 4 right angles. Any quadrilateral that has 4 right angles must be at least a rectangle, if not a square. So we relate to quadrilateral GMBL as a rectangle. The opposite sides of a rectangle are equal to each other. That is to say, side GM equal to side BL. GM equals to BL. So here, side GM equals to side BL. Repeat again. The opposite sides of a rectangle are equal to each other. That is to say, side GM equals to side BL. But we already found out that GM is the diameter of the circle. And from this equation, we derive that BL is also the diameter of the circle. The radius of the circle is x, therefore the diameter is twice as long as the radius. That is to say, the radius BL equals to 2x. Here the radius, the diameter BL equals to 2x. Here BL equals to 2x in its length. Okay. In the next step, we extended the perpendicular LG until it touches the side DM at point K. Then we proved that the right triangle KLM is similar to the small right triangle ABM. Why those two triangles are similar to each other? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. In addition, this is angle theta, that is a common angle that belongs to both triangles, so therefore angle theta equals to itself. And here also, if we focus on triangle KLM, this angle equals to theta, this angle equals to 90 degrees, therefore this angle must be equal to 90 degrees minus theta, as I already explained it, not repeat on it. So those two angles are both equal to 90 degrees minus theta, therefore they are equal to each other. So I actually found out that all the three angles in the big triangle KLM are corresponding equal to all the three angles in the small right triangle ABM, therefore those two right triangles are similar to each other according to angle similarity rule. And from the fact that they are similar to each other, we conclude that the following relationship exists between their sides. We conclude that ML in the big triangle over MB in the small triangle equals to KL in the big triangle over AB in the small triangle. I repeat again, we conclude that ML over MB equals to KL over AB. ML, I already explained it before, that ML equals to 8 over 3 plus 2x. You see it from lowering. So we substitute ML by 8 over 3 plus 2x. Over MB equals to KL is the missing side. Over AB is 2 according to what is given as the question. So 8 over 3 plus 2x over MB equals to KL over 2. MB is 8 over 3, so we substitute MB by 8 over 3. In conclusion, we found out that here we did a common factor, we multiplied 2x by 3 and then we divided it by 3 in order to have a common factor of 8 over 3. So 2x times 3 is 6x, so we have 6x plus 8 over 3 equals, over 8 over 3 equals to KL over 3, KL over 2. We have 3 in the numerator and 3 in the denominator, so 3 will get cancelled. And finally we found out that 8 plus 6x over 8 equals to KL over 2 because multiply this equation. And finally we found out that 8 times KL equals to 2 times 8 plus 6x. We divided this equation by 4, we divided this equation by 2, and found out that 8 plus 6x equals to 8 over 2 is 4, so it is 4 KL. 8 plus 6x equals to 4 KL. We divided this equation by 4 and finally found out that KL equals to 8 over 4 is 2 and 6x over 2 is 1.5x. So in total KL equals to 2.1.5x. Here we can write down that KL equals to 2 plus 1.5x. We already found out that triangle KLM is similar to triangle ABM, therefore you can derive it, from the fact that those two right triangles are similar to each other, that the following relationship exists between their sides. That ML in the big triangle over MB in the small triangle equals to KM in the big triangle over AM in the small triangle. Repeat again. ML over MB equals to MK over MA. Again, ML, we have already found out that ML equals to 8 over 3 plus 2x, so we substitute ML by 8 over 3 plus 2x. ML equals to 8 over 3 plus 2x, so we substitute ML by 8 over 3 plus 2x over MB. MB is 8 over 3, so we substitute MB by 8 over 3, and is equal to MK. MK, it is very easy to see from involving that MK equals to MA plus AK. MA is 10 over 3 plus AK that is unknown. So we substitute MK by 10 over 3 plus AK. We substitute MK by 10 over 3 plus AK plus MA. MA is 10 over 3, so we substitute MA by 10 over 3. Then we multiplied 2x by 3 and then we divided by 3. And we multiplied AK by 3 and then we divided by 3 in order to have a common factor here, 10 over 3. So here, 8 over 3 and 2x times 3. 2x times 3 is 6x over 3 over 8 over 3 equals to 10. AK times 3 over 3, so AK times 3 is 3AK over 3 equals to 10 over 3. We have 3 in the numerator, 3 in the denominator, so 3 will get cancelled. We have 3 in the numerator, 3 in the denominator, so 3 will get cancelled. And finally we get that 8 plus 6x over 8 equals to 10 plus 3ak over 10. Here we cross multiply this equation. We found out that 10 times 8 plus 6x equals to 8 times 8 plus 3ak. We open the brackets on both sides of the equation. And finally we found out that 10 over 8 is 80, plus 10 plus times 6x is 60x, equals to 10 times 10 is 80, plus 10 times 3ak is 24ak. So here we have 80 on both sides of the equation, so 80 will get cancelled. And finally we found out that 60x equals to 24ak. We divided this equation by 24, and finally we found out that ak equals to 60x over 24, it is 2.5x. AK equals to 2.5x. Okay, then I copied for the other AKBL and we analyze it. This is the triangle AKBL that I copied from the original drawing. this is quadrilateral AKBL that I wrote on the original drawing. Inside quadrilateral AKBL, we have this circle that is blocked by the quadrilateral. So I call it the circle that is blocked. And then I presented to you rule number 2 and we implemented rule number 2 in our drawing. According to rule number 2, the lengths of two tangents from a common external point to a circle are equal. We have the common external point P. From point P we draw two tangents to the circle, tangent PA and tangent PB. And according to rule number 2, this rule number 2, the length of PA is equal to PB. PA equals to PB. So we can implement rule number 2 in our drawing. If you focus on the common external point A, we have two tangents to this circle. Actually here, this circle is tangent to the quadrilateral KBL at 4 points, L, M, N, and O. So we have the common external point A. From the common external point A, we have two tangents to this circle, tangent AL and tangent AM, and according to rule number 2, they must be equal to each other. That is to say, AL equals to AM, AL equals to AM. So if AL is A, then AM must be also equal to A. Then we focus on the common external point B. From the common external point B, we have two tangents to this circle, tangent BN and tangent BM. And according to rule number 2, they must be equal to each other. That is to say, BN equals to BM. BM equals to BN. So if BN is B, then BM. If BN is B, then BM must be also equal to B. Then focus on the common external point L. From the common external point L, we have two tangents to this circle, tangent LN and tangent LO. And according to rule number 2, they must be equal to each other. That is to say, LN equals to LO. So if LN is C, then LO must be also equal to C. And finally, we focus on the common external point K. From the common external point K, we have two tangents to this circle, tangent KO and tangent KL. And according to rule number 2, they must be equal to each other. That is to say, KL equals to KO. KL equals to KO. So if KL is D, then KO must be also equal to D. And then we actually added AK, side AK to side BL. Here, AK, what is the value of AK plus BL? AK equals to A plus D, so we substitute AK by A plus D, plus BL. BL equals to B plus C, so we substitute BL here by B plus C. So in conclusion, we found out that AK plus BL equals to A plus D plus B plus C, so we can change the order of the variables here, and we get that AK plus BL equals to A plus B plus C plus D. Then we added side AB to side KL. Again, we added side AB to side KL in quadrilateral AKBL. AB equals to A plus B. So AB equals to A plus B, so we substitute AB by A plus B plus KL. KL is C plus D. So we substitute KL by C plus D. So in conclusion, we found out that AK plus AB plus KL, AB plus KL equals to A plus B plus C plus D. So both AK plus BL and AB plus KL equals to A plus B plus C plus D, therefore they actually equal to each other. So you can write down that AK plus BL equals to AB plus KL. So here we have AK equals to 2.5x. So we substitute AK by 2.5x. BL equals to 2x. Therefore we substitute BL by 2x. AB equals to 2 according to what is given in the question. So we substitute AB by 2. And finally, KL, we found out that KL equals to 2 plus 1.5x. So we substitute KL by 2 plus 1.5x. In conclusion, we found out that 2.5x plus 2x equals to 2 plus 2 plus 1.5x. 2.5x plus 2x is 4.5x. 2 plus 2 is 4. plus 1.5x. We substitute 1.5x from this equation. 1.5x plus 4.5x minus 1.5x is 3x. So 3x equals to 4. We divided this equation by 3 and finally found out that x equals to 4 over 3. The radius of this circle equals to 4 over 3 units. And we know that the area of any circle, that square bracket is the sign for the area. The area of any circle equals to pi times the radius squared. Okay. The radius in our circle is x, so the area of the circle equals to pi x squared. But we just like now found out that x is equals to 4 over 3. So we can substitute x by 4 over 3. If x is 4 over 3, then x squared is 4 over 3 squared. So the area of our circle equals to pi times 4 over 3 squared. 4 over 3 squared equals to 4 squared, that is 16, over 3 squared, that is 9. So in conclusion, found out that the area of our circle equals to 16 pi over 9 square units. Or in terms of numbers, it is equal to 5.585 units. I repeat again, the area of this circle equals to either 16 pi over 9 square units, or in terms of numbers, it is equal to 5.585 square units. Okay, thank you very much.